welcome to the TIA Centre Seminar Series. So here we invite speakers to give a presentation in the area of computational pathology. So I think this is our 5th seminar now. So anybody who's coming here for the first time, you're more than welcome to also join in the future as well. So today, very pleased to welcome Narmin to give a presentation. So Narmin is a research scientist and software engineer in the Cath Lab at RWTH Aachen University in Germany, which is in the heart of Europe. And her main responsibilities are the development and improvement of artificial intelligence algorithms for digital pathology images. She graduated from Friedrich Schiller University in Germany with a master's degree in medical photonics and has more than 5 years program experience, including 2 years working in industry. And her main interests lie in explainable and trustable AI medical applications. So hopefully I've set the scene there for you, Narmin. And yeah, we're looking forward to your presentation. Just for everybody else on the call as well, we would encourage anyone who has any questions to raise their hand or to type into the chat, and we'll field those as we go. So looking forward to having you, and please start when you're ready.
Great, thank you for a nice introduction. Okay, then I will, can I share my screen?
Yeah, I need to make you host.
Thank you.
Yep, you should be able to do it now.
Perfect, yeah. You see my screen, right?
Yeah.
Perfect, okay. Thank you for the invitation, definitely. I'm so happy to be here, and I hope that you will enjoy the presentation and that we can have a nice discussion today. So as you are seeing, I mean, the title that we somehow have for this talk is Benchmarking Artificial Intelligence Methods for End-to-End Computational Pathology, which is the title of one of our papers which we submitted in the last year. And we are still waiting for the reviews, but today I want to somehow discuss with you about this paper, and of course I will discuss about some other papers, and we will go through different categories and topics. But just before starting, I would like to somehow just briefly introduce myself. So I moved to Germany in October 2017. I moved to Jena, a city in East Germany, and then I did my master in medical photonics there. But I had a chance to somehow work in different research institutes there. And the most important one was somehow I worked in Carcinoma Meditech AGA for 2 years, and I wrote my master thesis there in the title of OCTP scan segmentation using deep learning, which was somehow the starting of this big journey, which somehow helped me to join Jakub Kata's group, research group, in 2020 October to do my PhD here. And so far, happily, I'm working here and of course, learning. About our group, probably most of you already know Jakub's group, and we are somehow a very young and interdisciplinary group of medical students and also computer scientists that we are trying to, by implementing artificial intelligence methods to defeat the cancer problem. Although the main data that we are using are digital histopathology, but of course we have also some other data like the endoscopy and MRI images. And as you know, we are located in EVTA University Hospital in Aachen in Germany. Okay, so going to somehow, and I mean, you can always just interrupt me and ask any questions. So I would like to have it like a discussion and not just presenting something. So for starting of this presentation, I would like to somehow categorize all the tasks that we can do in digital histopathology into 2 groups. So I have this image from this nice review written by Echle, which the first category is somehow basic image analysis, or let's just call it low-level tasks. So this type of tasks like tumor detection or subtyping or grading, The reason that I am calling them basic image analysis is because the way that we generate ground truth data for this type of task, the way that the pathologist is actually generating ground truth data for this type of task is actually just by looking to the whole slide image and then giving us this ground truth data. So exactly in the same way, we give the input to the whole slide image, and we are sure that this data, the features that we are searching for is somehow is present actually in a whole slide image, and then we are asking the network to give us the prediction. So it was the main topic for years, and many papers are published in the thing, like for example, segmentation, or even cell quantification, for example, or cell type classification. So all this type of tasks are something that the pathologist also can look to the whole slide image and give us this information. The second category that I want to talk about it, I want to call it advanced image analysis, or maybe higher level tasks. So this type of tasks is different from the one that we already talked about it, like for example, survival prediction, response prediction, or mutation prediction. Why they are different is because the pathologist is usually not able to just by looking to the whole H&E whole slide image tell us this ground truth data, and usually we need some external tests and experiments to somehow get this type of information from the whole slide image. So we call them just advanced image analysis tasks, which so far we know that deep learning works also very good in this field, but we will somehow look at more details to this kind of task. From the other point of view, I want to classify somehow our approach to the digital pathology field from the computer science somehow point of view, how we can somehow perform these models. So of course, this first somehow stage is providing the data, of course, the tissue or resection, and then we generate the slides. We use a slide reader to somehow digitize this image, and then we have our whole slide image saved in our computer, right? So there are two approaches. First is handcrafted AI approach. What I mean there is somehow we have some pre-assumption that which features can be useful to predict this target which we have in mind. So we use either a pathologist or oncologist or somehow experts, or even we can use somehow computer programs to extract the specific features from the whole slide image. And once we have these features, we use them to train our model. So actually we limit our model. We somehow give some pre-assumptions that I do believe this kind of features are important for this prediction, and please use them. The second approach, so this handcrafted, I can call it maybe older somehow approach, and then the much newer approach that we are using mostly these days, and most of the papers that are submitting these days is using this new one, is deep learning based approach, which there somehow we give the image and we ask for the output. So we don't define the features. And we expect the network to go and learn that specific features actually from the image based on the target that we are defining for the network. So no matter which approach we are using, at the final somehow layer, we are getting the output for that model, which we need to somehow compare it to the ground truth data that we have, and then report the performance of our model, that how it is performing actually. So now I will somehow talk about some examples for each of these categories that we discussed. The first one, as I mentioned, is handcrafted AI approach. So I have here two papers. The first one is prognostic value of automatically extracted nuclear features in whole slide image, which actually published in 2012. So what they did is actually they generated one automated nuclei segmentation, and they applied it on the TMAs that they had as a data set. and they generated the area of the nuclei in this image and the standard deviation of that. So as I mentioned before, I mean, they, based on the studies that they did, research that they did, they were sure that somehow the nuclei feature is important for this prognostic features in breast cancer. So they did know that, and they extract these features, and at the end they actually proved that yes, the assumption was true, and they were able to predict the somehow prognostic from the nuclei features. The second paper has somehow the same approach, so but in a different cancer type. So again, they are extracting many features from the nuclei, and based on the feature selection, they are selecting, as I remember, 5 main important features, and then they are using this for survival prediction. So this kind of approach are actually working very well. We already saw a lot of papers based on that, but it needs a little bit pre-processing. It needs somehow, first of all, to know that which features are important, and then to extract that features from the whole slide image precisely, definitely. But let's talk about end-to-end approach, which, as I said, is now maybe the trend somehow among all the people working in this field. What you are seeing in this slide, I will call it classic approach, traditional approach. So this is not the must now, but this is somehow the starting point, I think, in this field for the end-to-end approach. So we have our data, we have our digitized whole slide image, and as you all know, we are not able to use this high resolution image as an input for our networks or our models. So we need to tessellate them with a specific resolution and the patch size to the smaller tiles or packs or whatever that you want to call it. This somehow intermediate step, which I called it as an optional, is actually annotation. Why I call it optional is because many studies showed that it is not improving the performance. So although it is very time-consuming process, it is not actually improving any improving significantly the performance. On the other hand, many other new techniques, like for example, multiple instance learning, they are actually able to detect the important part of the whole slide image and learn the target only from that part. So actually, this is just now somehow an optional step in this whole end-to-end approach. But of course, based on a specific target, if someone somehow believes that the annotation will improve the performance, definitely it is somehow a useful case. After that, it comes to the normalization. So it's because whole slide image coming from different institutes and different hospitals have different stain materials, and then they have different slide readers. So usually they have different color normalization. So to remove any kind of bias there, we usually normalize the color distribution in these tiles. And then we move to this assign step, which again, I somehow put it inside the box because this is again in a traditional approach. What we do is that we assign the label of whole slide image to each of these patches which we extracted from the whole slide image. But however, for example, as we will discuss in some new approach, we don't need this step. But let's just for now assume that we are assigning the label of whole slide image into the patches. Yes, go ahead. I see a raised hand.
So I was muted then. Yeah, I thought I'd ask a couple of questions on this slide. So just wondering, what's your experience with stain normalization? Do you always use that in your research group, or have you thought about using potentially other techniques such as color augmentation, stain augmentation?
So far, we are using just color normalization, but there are a lot of actually discussion between us that we have to somehow move from normalization to color augmentation, because I personally do believe that somehow this is better way of generalizing the models based, because also this normalization step takes a lot of time, at least somehow with the script that we are using. It's actually a little bit time consuming step, which I do believe by just color augmentation, we can just skip that step.
Okay, so do you pre-normalize all of your image tiles? So you extract all your tiles, you normalize them, save them on disk, and then you process those tiles?
Yeah.
Okay.
Yeah, exactly.
Exactly like you say, when you do it on the fly, it can be quite time consuming, can't it?
Exactly, yeah.
Okay, and so you're mentioning here that you tessellate all of the whole slide images into a series of tiles.
Mm-hmm.
So do you think this will be always what happens in computational pathology, or do you think maybe there'll be some cases where you will need more spatial information?
I hope it will not actually, because I mean, I think we are all aware of this, that while doing this, we are losing this special information and somehow the connection between the cells and tissues. And because I think when pathologists actually look at the whole slide image, so they look at the beginning to this whole somehow image, and then they zoom to the part that somehow they feel that it's more important, which actually there are papers that they did this, and that they have the somehow first very overall look, and then they zoom into the area of the interest, and then they somehow classify just the image, the tiles from that part. So I hope that somehow we will find a better way to go from the whole slide image to somehow the prediction. But so far, I think the vision transformers actually will help us there. But the point is, I'm actually thinking a lot about that approach. But the point is that's also limited because of this huge size that we have. So, but yeah, I somehow see some hope about vision transformers to be able, because there also we have this special information, the connection between the tiles. I mean, we will talk about it today a little bit, but yeah, definitely.
Okay, brilliant. I think you can continue now, Narmin. I think we've got one more question.
I
Alex?
see another question.
Oh, Alex, you're muted.
Yeah. I was also wondering, like, for example, do you think that something like overlapping tiles, or a certain size of the tiles, or like a certain amount of tiles, like for example, using all the tiles, or maybe only sticking to, let's say, 50 tiles from one whole slide image per each? Like, do you think there are certain differences in the overall performance, or like where you just have, where it just doesn't really improve much more?
We tried it actually a lot. I mean, I don't have some, we never published a paper like that for that, but we tried overlap tiles. It didn't change the performance. I mean, we somehow used 25 overlap, and then I think 50% overlap. So it didn't change the performance, because I think what is missing here, and what somehow can improve the performance, if the network somehow learns that, I don't know, that after stroma, I mean, maybe the connection, this layer of stroma and tumor, for example, that part that when it sees that somehow how this tumor is, for example, invasive into the, for example, stroma, you know. But when we are doing overlapping, again, it's somehow just a random selection of these tiles, and I think we are losing this information. So we tried, for example, overlapping, but it didn't improve it. And also, I think we tried in many approaches also different tile size, even sometimes very big tile size. But so far, we never somehow came up with some result that's saying that, wow, doing that is really somehow changing the performance.
Okay.
But I definitely think, I mean, if we find some way to somehow keep this special relation of the tiles together, that would be at least, you know, from the human point of view, I think it will make more sense to somehow.
Yeah. Yeah, thanks.
You're welcome.
Right, please continue, Narmin.
Okay, great. So yeah, we assign this whole slide label to the smaller paths, and then we train our network. But again, we come to this somehow a step that we need to aggregate our results. So we have now scores per each tile, because we somehow assign the whole slide label to these tiles. So we need to find a way to somehow aggregate the scores from all these tiles to go to the patient-wise scores, because at the end we want a label for a patient, right? So again, this step is not required, for example, in multiple instance learning, but in any case, I just wanted to mention it, that in classic approach we have it. But of course, when you are happy with your model, it is always useful to validate it on some external cohort to just see that whether it is performing also good there or not. Okay, but why end-to-end approach is really nice, is fascinating, and is actually very useful is because in contrast to somehow this handcraft feature extraction, we don't say anything to the network. So we don't say that what is important, which area, go and check it. But network actually look at all the tiles that we are giving, and this is the network which tells us what I saw there, that I am saying that this patient's label is what I am saying. I mean, the prediction of the network. So this time is the network which is actually helping us to understand that which features inside the whole slide image was more useful to predict the target. I have, for example, which we call it, I mean, before forgetting that we call this somehow output of the network as a prediction heat maps, which usually, let's say it's blue, from blue to red. Usually blue is really high score tiles and the red is very high score tiles. And then we can always find out that which part of the whole slide image was more informative. I have here two examples that one is published in 2019 by Cortiel. I hope I'm spelling that correct, but they somehow prove that stroma, inflammation, and cellular diversity were very important in predicting survival in mesothelioma patients. So this is very interesting because they didn't somehow provide this information to the network, but at the final somehow evaluation of their results, they actually see this information from what they are getting from the network. Or for example, in 2018, Mubadder Sani, it's with the same somehow approach, see that the microvascular proliferation is very important and is associated with a poorer outcome in glioma patients. So this is, I actually personally find it very fascinating that the end-to-end approach can give us some information that either we didn't know or we didn't think of it, or we did know and actually it proves what somehow our pre-knowledge. I want to talk about some examples from simple tasks to this advanced task that we said, and then of course I will go to the paper that I already mentioned at the beginning. So this paper is published in 2020, and this can be categorized as the simple task, which I said. So it is grading. They have 6 outputs. First, they are classifying to the benign and malignant, and then from the malignant ones, they are somehow predicting these 5 categories for the grading. And as you are seeing with the area under the curve of 0.98, it is performing great. So these are all end-to-end approach. You just give the image and you ask for the output, and as you are seeing, it is performing pretty well. The other approaches, for example, survival prediction, again, in an end-to-end approach. So this paper is also published in 2020. They have this masks to just ignore the background, which is not actually a difficult thing. But then they are randomly selecting this samples from the whole slide image. When I was reading actually this paper, it was so interesting for me that they had a big paragraph about somehow saying that why it is not a bad idea to select this random tiles from the image. And they were somehow mathematically proving that when you are selecting randomly tiles from the whole slide image, the probability that you don't get any informative tile from the whole slide image is really rare. And then they were saying that the annotation is very time consuming and we should not somehow limit the network to just see one part of the image, and we have to somehow provide all tiles. So they have actually a very big paragraph to say and supporting that why it is a good idea to select this random tiles. But anyway, they are doing the same thing, and they are giving this smaller patch to the CNN, convolutional neural network, and based on a specific loss function that they decide, they get this 4 somehow categories for the risk of the patient. And as you are seeing from the Kaplan-Meier plot, actually with a significant p-value, they are able to classify people into 3 low, medium, and high risk groups. So again, we are saying that for survival prediction, although from my own personal experience, survival prediction is very difficult from whole slide image, but at least in their case, it is working pretty well. The other task that we saw a lot is, for example, mutation prediction. So, for example, this is categorized in this advanced image analysis task because it is not a part of routine somehow pathology that the pathologists look at the whole slide image and predict the mutation from that, but we need extra tests for that. But as Jakub Ketta somehow in 2019 came with this fascinating idea, and he tried to predict the MSI microsatellite instability directly from the histology image. And yeah, and as at that time with the AOC of 0.84, it was performing pretty well. Another mutation prediction, again from our group, which is published by Löffler in 2021. And as you are seeing again with the, these prediction maps, which I somehow mentioned. So in this end-to-end approach based on the heat maps that you are generating, you are actually able to see that which part of the whole slide image was more useful for that type of prediction. And the last example is this recent paper from Faisal Mahmoud's group, which published by Lou, and it was a very nice idea, and probably you all know it from his presentation, which they somehow try to predict the origins for the cancers of unknown primary. And again, I want to somehow emphasize about the heat maps because, for example, in this example that I have here, they try to predict the colon cancer from lung, lymph node, and then the liver. And then they saw from the heat maps that they are generating that actually network is detecting this, for example, different size of glands, which are the specific features of the colon cancer, and many other features which are somehow specific for the colon cancer. So network actually saw that and detected that features also, as we as a human already did know it. So this is why I want to somehow emphasize that end-to-end approach is actually very nice. It is easier to provide everything. Of course, it is difficult to train it, but if you succeed, then what you are getting as an output of the network is, of course, very useful, and it can somehow give you the information which maybe you didn't know, or as I said, you didn't know it, and it is just a proof of that. But how fast are we growing? So if we look at the just machine learning papers, as I read in one of the blogs, it's just 100 papers per day. It's too much. And even if you want to somehow look specifically about artificial intelligence and digital histopathology, so you always see these curves that the number of published papers is increasing and increasing, because from one side, the computer science, pure computer science techniques are increasing, and we are using them in this digital pathology field. And then, so the number of methods and number of targets and number of tasks that we are using and predicting is increasing. And somehow, sometimes it's getting confusing that which method should I use for the specific target that I have in mind. So this is somehow the main motivation that we had for this side project during my PhD, to just compare different methods and see that which one is performing better. And of course, we hoped at the beginning that one of these methods will somehow work the best for all the targets that we are classifying, and we will say that, so that should be the somehow best model to somehow use it in this type of at least targets. But we will see that somehow it was not the case. But anyway, so we selected 5 recent successful models, and we tried their performances on different clinical relevant targets. Before going to the results, I want to just, for each of these methods, just one slide talk about that, how they work and what is their background, to just get to know that how they actually work, and then we will go somehow to the data set and the results behind this paper. So let's start with the ResNet, which is the older one. So ResNet is actually published first time in 2015, and as you're seeing, it has been cited by almost 100,000 papers. So it was totally a success at that time, but the idea that somehow they had in mind, at that time they did know that as much as the network is deeper, it is performing better, and because it's extracting better features and it somehow know the data, know the image better. But they also did know that, I mean, as you're seeing also in this image, when you somehow increase the number of layers from 20 to 56 layer, the training error increase a lot, and also the test error. So it was not easy to train deeper networks because of the problems that you are also seeing, the converging problem, vanishing gradients, and accuracy saturation, which each of these topics is somehow a big issue, and I don't want to somehow go into the detail. But because of these problems, they were not able to somehow simply train the deeper networks. So they came up with a brilliant idea of using this skip connections. And if I want to just in one very simple sentence explain the idea of this somehow skipping connection, is that they were adding the output of previous layer to the output of the current layer. In any case, if this somehow the block of layers were somehow destroying the performance and making the higher error, then you could actually, by putting fx is equal to 0 and forcing the network to have weights and biases for all of that layer somehow to have the 0, you were actually, it was like doing nothing there, right? You were somehow just transferring the output of the previous layer to the next layer. So using this idea, which mathematic behind it is of course very complex, they were somehow trying to, I mean, they actually succeed to train deeper networks. And as Jakub Kata somehow showed in one of his papers, ResNet 18, so this ResNet has, I think, from 18 to 100, so it's different layers of the convolutional neural networks. And he somehow showed that ResNet 18 is performing better than all other networks like VGG and then ISQuestNet and AlexNet, based on the number of parameters and the time that you need to train network. So I got from here ResNet 18, and this is what we will use in this paper to compare its performance to the other models. EfficientNet. EfficientNet is a little bit published later than the ResNet in 2019. The idea that they had was that, so it's the same theory somehow, it's the same story. They also know that as much as the network is deeper, it is better. But the question that they had in mind is that how actually we should scale up the network. I mean, what is the best way of doing that? It's just adding layers, and or somehow is it the depth of network, or is it somehow the width of labels, so bits of the model? So how they should actually scale up the model. So this is somehow the idea that they had in mind. So they came up with a very basic convolutional neural network. They named it EfficientNet B0, and then they scale it up until B1 to B7. So the B7 is the biggest one. And then as they are reporting in their results, this EfficientNet B7 is performing much, much better than all other EfficientNets, and also in comparison to the other ResNet and except and all other networks. So from here, I got EfficientNet V7 pre-trained on the ImageNet. Also, the ResNet was actually pre-trained on ImageNet. So from here, we got EfficientNet V7 pre-trained on the ImageNet to our comparison. Then we jump to the vision transformers. So probably you are hearing these days a lot about transformers because they are amazing and they are somehow the dominant approach in the natural language processing, and they are performing very well. In this paper, which is submitted to arXiv in 2020, they actually use this initial transformers and they somehow used it for image classification. If someone want to actually learn about transformers, I would definitely recommend this thing, which somehow I wrote it. So it's in Toward Data Science website, and they are illustrating the transformers in a very simple way and with a nice illustrations. I really enjoyed it when I was reading it. So I would definitely recommend it. But again, if I want to somehow say in one sentence how and what is somehow the transformers and how they work, is that you give one sentence, just imagine, or sequence of the words, and the network itself, based on the attention that it's getting from each of these words, learns that which word in the sequence is more important for me for that specific prediction. So in this paper, they got the same idea and they use it for the image. The problem was that they needed to go from the 2D dimension of the image to 1D. And actually it was simple. They had just one linear projection and they were just flattened somehow these small patches of the image. So the idea was actually not that much difficult, but it was very fascinating that they used it and they showed that it is actually performing very well on the ImageNet. So from here, we get the vision transformers trained, again, pre-trained on the ImageNet, and we will use it in a paper. The next one is MIL, or multiple instance learning. And I know that from Faisal Mahmoud's presentation, you already know this one and the next one. So I don't want to spend a lot of time on it, but MIL is actually very old somehow idea, and it comes, I think, from 90s somehow. But I mean, the mathematics behind it. But somehow this paper, which I mentioned in the first line of this presentation, it actually is one of the first papers which used multiple instance learning in digital histopathology, and they somehow showed that it is performing very nice. The idea behind this, so I just want to say that the classic MIL was designed actually only for binary classification. So the idea behind this is that I have one bag full of instances. In our case, I have one polyslide image, which there are many paths which I can extract from this whole slide image. The label of this bag is positive if at least there is one instance. In our case, at least there is one patch inside that bag which has the label of positive. If there is nothing, then the bag is negative, and I'm sure everything inside the bag is also negative. So the idea is amazing for our case because we don't know the label of tiles always, right? So we, and this classic approach which I mentioned, we actually assign the whole slide image label to the tiles, but this is a noisy way of doing that. But in this case, somehow we don't pre-assume the label of the tiles, but we actually assign one label to the bag, and then we train the network using this bags. So we got this naive, somehow multiple instance approach, and again, we will compare its performance to the other networks. The last one is CLAM, which again, you know it already, as I mentioned, it's published in Faisal Mahmoud's group by Lou in 2021. This is somehow similar to the multiple instance learning, but it uses somehow attention-based pooling instead of max pooling. And they also have this additional clustering approach. So during the training, they are somehow assigning pseudo labels based on the attention scores that they are getting from the tiles. They are assigning these pseudo labels to the tiles. They are doing this clustering, and they are adding the loss of this clustering to the main loss function that they are generating and trying to optimize it. So, and the heat maps, I mean, generated by this paper that probably you all saw them previously, are amazing. And as you are looking in more details, you are seeing that the network actually find out the regions of interest, which we also were expecting it somehow. Okay, so now we know all the methods. Yeah, go ahead.
Yeah, so I just wanted to have some clarity, also for the sake of the listeners. So on that wheel, you had ResNet, you had EfficientNet, and then you had MIL. So there's an overlap there, right? So ResNet can be used in MIL. So can you just maybe clarify, when you say ResNet and when you say EfficientNet, is that trained in a fully supervised setting?
I can actually, maybe in the next slide, I can actually explain it, but I can actually tell it now. So for MIL and CLAM, we are using features extracted from the tiles. So we don't use directly the tiles. So we give the tiles to the ResNet, for example, as an initial step. So let me say that like that. So ResNet, if you are training it, so for example, on ImageNet, you have 1,000 outputs for that ImageNet, right? But before that 1,000, before that output layer, we have, for example, 1,024 numbers, let's say. So we have one vector with a length of 1024 in ResNet 50, which we call it feature vector for that specific image. So what has been done in MIL and CLAM is, before doing anything, they are extracting features for all the tiles of the whole slide image. So now instead of one tile, we have one vector with a size of 1024. So it is just numbers. So they are extracting these feature vectors for all the tiles, and then they are putting just these feature vectors inside the bag and not the tiles inside the bag. So actually MIL and CLAM is using ResNet as a feature extractor, and then they are using these feature vectors to train somehow the network. Was it clear, or should I?
Okay, yeah, that's pretty clear. So what would be good to know is ResNet and EfficientNet, right? So if you're not extracting necessarily a feature vector, then what would you have as your training target? Are you having the same training target for each and every input patch?
Yeah.
Yeah, is that what you're doing? Okay.
Yeah, exactly. Yeah.
Thank you.
Okay. You're welcome. Okay, so this is the targets that we used in this paper, and also you are seeing the data set. So we had 8 data sets. We used 4 of them with 4 different cancer types. We used 4 of them for the internal validation, and then we used the next 4 for the external validation. So we had here 1 renal cell carcinoma subtypes classification, and then we had 5 mutation prediction. And as you are seeing, we used 1 TCGA in somehow all of the cancer types that we had, and then another data set that we already have in our database. As you are seeing here, I mean, as I mentioned, so we do first the k-fold cross-validation, which in this case, it was just 3-fold cross-validation. And then we report the results for that. And then we used all the patients in that data set to just train 1 model. And then we use that model to validate it on the validation data set. So as just right now we talked about it. So in ResNet, EfficientNet, and Vision transformers, we assign the label of the whole slide image to the each tiles that we had. Then we select randomly some tiles from whole this somehow huge number of tiles that we had. And then we trained our network based on, I mean, each network somehow does what it somehow does during the training. And then we get the tile level prediction. And as I mentioned beforehand, we aggregate the tile level prediction. We just average them to get the patient level prediction. However, in the case of MIL and CLAM, the approach is different because, as I mentioned just right now, here we use ResNet 50 to extract the features from the tiles. So after this step, we are not working anymore with tiles, but we are working with this feature vectors for each tile. And then we put all the tiles from one whole slide image inside one bag, and we say the label of the bag. And then each of these methods, so CLAM and MIL, again, based on their approach and what is already designed on their network, they are trying to find out that which tiles or which feature vectors are actually more important. Yeah, go ahead.
So we have a question from Kashif, and Kashif has asked, how do you determine the number of samples that you randomly sample?
We actually have this somehow 500 magic number in our group that we are using that. But if you're asking that if I evaluated the different number of somehow tiles, so far, no. I mean, I didn't somehow try it, how it works if I selected 100 random tiles or I don't know, 1000 random tiles. So somehow it is as a predefined as 500 tiles, and because it's working good, so I used it the 500, this magic number, but actually I would like to maybe try different number of tiles for this paper at least to see that whether the performance is decreasing by, or I mean when it starts to decrease, because I'm sure that it will start to decrease somewhere when I'm decreasing the number of tiles.
Yeah, it might be also interesting to first do a clustering. So maybe do a clustering as an initial step and then randomly sample, let's say, N samples from each cluster, because then you know that you're not missing anything there.
Yeah, exactly. That's something that interesting, but we talked actually in our group that would be a nice thing to do, to somehow cluster the tiles into different and select from each cluster some number of tiles. Yeah, definitely. Okay,
I think you can continue, please.
Okay.
Can I have a related question related to this point?
Sure.
Did you try to run the same pipeline multiple times, selecting different 500 numbers each time, and how much was the difference?
You will see it, I think in 2 slides that it's in my to-do list. I didn't do that, but I have to do it. It is actually in my to-do list, you will see it. Because I mean, in one of the projects that we were doing, we actually saw that I mean, it is better idea to do this somehow n times repetition and find out the average performance, especially for a paper like this that you want to somehow report the performance. I mean, do you want to somehow compare the performance? So definitely, I do agree, and I definitely would do that. But this paper is still under the revision, so as soon as it comes back, we will do that. Okay, I think I have 10 minutes, right? I will try to be a little bit fast. So as a result, as I mentioned at the beginning of the presentation, so it was not the case that we say that this model was performing very well for all the targets. But we saw that for renal cell carcinoma, no matter what we are using, it is performing very well. So for the cross-validation, for the internal validation, the performance was always around 0.97, 98. And for the external validation, somehow a little bit lower, but again, very well. But no matter which one of the ResNet, ViT, CLAM, MIL, all of them are performing better. But for the mutation prediction, the performance was actually varied a lot between the models. For example, ViT and ResNet for the colorectal cancer was always significantly so outperforming other the models, but we couldn't somehow say the same thing for the gastric mutation prediction. But in general, somehow what we saw in our analysis is actually, I mean, using the classic approach and using ResNet and ViTs were performing much better than the other cases. As I mentioned, overall, it was so surprising for the mutation prediction. The MIL and CLAM was not actually performing very well that we were expecting. So but the reason for that, I do believe that should be discovered, and we have to somehow spend time there and somehow understand that what can be the reason for the poor performance there. But as I already mentioned, I have a to-do list for this paper, and it is not somehow finalized yet, at least in my mind. And then I would like, for example, add this attention-based multiple instance learning, because the multiple instance learning that we are using is this naive approach, and then compare it to the performance of CLAM to just see that what is the importance of this clustering step in the CLAM for the performance. And as we talked just right now, I would like to repeat the experiment n times, at least for the ResNet, ViT, and EfficientNet, because there I am selecting random tiles. So in MIL and CLAM, we are using actually all the tiles, but in this case, we are just selecting randomly 500 tiles, and then for each slide. And then I just want to make sure that it is not a matter of luck. I don't think so, but I just want to make sure that it's not a matter of luck to somehow get a good performance in some cases. But then, of course, I would like also to compare the performance of ResNet 80 to a deeper one to ResNet 50. It is classic approach to see that whether deeper network is performing better or not in this case. And also, I would really like to spend time and explore the heat maps generated by the CLAM for mutation prediction, because I really like the heat maps generated by CLAM, and I would like to somehow check them and see that what was the important for the CLAM in each whole slide image to somehow predict the output. So I have, I think, only just 3 slides, so I will not talk a lot. And these are just somehow 3 ongoing projects in our lab and some nice ideas that we want to spend time on them and do more research there. So the first one is actually submitted by one of our lab members recently. This is the farm learning, which, I mean, you already heard about it also, I think. So we previously had this local learning. Everyone had their own data set. They were training and they were reporting results. We were not happy with that because it was not usually, we didn't have usually enough data to get a good performance. So we put all the data together and we trained one model, which again is not easy because of this data sharing policies. So it is not also the best case to do. Then it comes the federated learning and swarm learning, which in swarm learning, what it is done is that the models are one model is training at the same time using different nodes, and the weights are getting simultaneously somehow updated, and it's shared between all the nodes which are somehow putting their data inside this training, which is an amazing approach, but I do believe that we need somehow the validation and variety of targets to explore this thing, but I do believe that it will somehow save us a lot of headaches in the future of this somehow data sharing problems. The next idea that I want to talk with you is this image text connection. So when I read, actually, there is a very nice blog for this paper, which is published. And when I read it, I really enjoyed it. And I wanted just to share it here, not just, I have some ideas that how I want to do it in digital histopathology, but I do believe that this is an amazing thing. And I think I somehow see some future projects in this paper for the histopathology field also. So just briefly explaining that what they are doing, they generated a big data set from the social media. It's not difficult, right? I mean, you can get, I don't know how many emails every day. But anyway, they get one data set from the social media. So it is an image, but the labels are not like ImageNet, cat, dog, plane, or whatever, but it is, I don't know, my funny, cute, blah, 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 blah cat. So it's somehow just that's natural stuff that we are sharing every day. So they have this image and they have two encoders. One is text encoder, the other one is image encoder. So text encoder, as I explained it in transformers, is actually going and finding that in the sequence of words, which word is important for this image. So this diagonal thing that you are seeing is actually the cat for the cat. And so it is finding that a specific word in that sequence of the text, and it relates that specific word to that image. And then they use this trained image and they call it zero-shot training. I don't know, I mean, how much you are familiar with that, but the point is, if we train a network on ImageNet for 1,000 targets, then we remember that I wanted to add another target. So usually network is not able to predict that external label. So what it is has been done now is the zero-shot training that you can the targets that you are predicting has nothing to do with the targets that you are training. So this is exactly what they gave a shot here, and they tried it. So then, for example, they moved to the ImageNet. So they have this 1,000 targets, which maybe was not actually included even in the training data set. And they created this artificial sentences from these labels, like a photo of a dog, a photo of a cat, or whatever. So this artificial somehow sentences, and then they used new image to predict the caption for the image. And as they are showing in many data sets, it's actually performing very well. I mean, they are training on totally different data set, and they are predicting totally different targets. And what they are assuming, what they are telling us is actually it is performing very well. So I really like the idea, and I think in future we will see using this somehow, this approach, and also in digital histopathology, of course. And the last thing that I want to talk is, of course, GANs, generative adversarial networks. We saw some papers related to that, but I do believe that somehow there is still a lot to do. So this is one of the example papers which published by our group, and one of our lab members somehow generated this synthetic image from their our observers to classify or somehow detect the synthetic image. So having this in mind, I think there are a lot still to do in this field, and I'm so happy actually to be here. But this is the end of my presentation. So if someone has any questions, definitely.
Great, thanks, Narmin.
You're
That was a brilliant presentation, really interesting and very thorough. So thank you very much for coming and giving the presentation.
Thank you for the invitation.
No problem at all. If you're okay, if we can field a few questions, I hope you don't mind us going a few minutes over.
Sure.
Okay, great. So Mustafa, do you want to go first?
Sure, yeah. Thank you, Narmin, for the great presentation. I really enjoyed it. So I had a question in mind about the depth of the classifier models that you used, ResNet and EfficientNet. I guess you've already mentioned something about it, that you're going to try different depths, different variation of ResNet in the future. I was wondering which variation of EfficientNet you use, because the power of the model really improves when you use deeper variations, like EfficientNet B7 is quite stronger than EfficientNet B0. So which one did you use?
I actually use B7. So I use somehow the most strongest one. But I mean, so maybe that's also some extra to do to add to this list, to somehow maybe also try the EfficientNet B0, for example, B1, I don't know, and the compare of it to the B7. But I mean, the point is, if you trust somehow the initial paper, so they are saying that B7 is performing very much better than the B1. So that was the reason that why I selected somehow B7 pre-trained on the ImageNet, and I used that one for the.
Yeah, maybe for your application, a smaller network work better. I mean, it's just a matter of testing. And I also had a general comment on those two pipelines that you're working on. So So you were wondering why using ResNet is working better. So to me, if you go to that slide, so
Sure.
to me, that approach also is some sort of MIL. I mean, the only different is the way that you aggregate the results on patches and the way that you sample patches. But anyway, if I understand it correctly, in the left approach, you also train the encoder during your training, right? That might be the reason that the encoder, right, ResNet, is training better, is trained to extract better features. Rather than the one that CLAM or MIL is using on the right-hand approach. So it's just a general topic. If you have like had that in mind, or have you discussed it? Have you considered it that maybe this would be the reason that the left-hand approach works better?
The point is we use the same somehow ResNet to extract the features here, but what in a paper CLAM somehow they are saying is that the features extracted by ResNet 50 pre-trained by ImageNet is actually sufficient. And what I heard also in Faisal Mahmoud somehow talk, that he was saying that because now recently people is started to use this feature extraction by self-supervised methods. But what I heard actually in his talk, that he said that they somehow came to this conclusion that actually features extracted using ResNet is actually enough for training. So this is something that I think probably, yeah, there is a still place to investigate. Yeah. But I understood.
So then maybe on the flip side, instead of thinking about training the whole encoder for, let's say, CLAM and MIL, you could maybe do an experiment where for the ResNet-based experiments and for your vision transformer experiments, you could freeze ImageNet weights there and only train the classification or transformer layers.
Okay, yeah, sure, yeah.
Great. Any more questions?
Yeah, can I have?
Please go ahead.
Yeah, just one comment based on the Mustafa comment that the left-hand side approaches are similar to MIL. Yeah, they are similar, and only difference is we can combine them all under one word, that's weakly supervised. But yeah, in MIL, you would fix that how much for aggregation are you going to use one patch in a bag or multiple patches in a bag. And for all others, the left hand, the ViT, vision transformer and ResNet based, there is multiple patches. If we take the majority vote, or yeah, that we are considering multiple patches. One comment is you haven't separated out tumor tiles from your data set for MSI prediction, which is actually a subtype of tumor. So when we include normal, so there is the differentiation that we would learn would include a lot of other subtypes from the tissue. And that could be one of the reasons that CLAM wasn't able to work better, because in CLAM, they have to sort out many clusters of tiles. If it is just run on the tumor tiles, maybe the difference of two performances is closed. So have you investigated that?
That's actually a very nice idea. No, because I mean, in the ResNets and in this classic approach that we are trying is somehow this noisy labels is usually acceptable because we have a lot of data and we somehow assume that the network will learn that somehow there are some noise in the data set. And as we are seeing, it's actually performing very well. But probably for CLAM and MIL, you are right. And even but then I think if we somehow want to annotate all the images, then we have to use that annotations also for the ResNet and ViT, because then I do believe, if we want to compare the performances, everything should be somehow the same. But the annotation is difficult, right? I don't know whether we have somehow that capacity to ask someone to annotate all that image that we have, but maybe we can actually train a classifier to not maybe a lot accurate, but to somehow train a classifier that can somehow give us this tumor part of the whole slide image and use only the tiles from that part.
And one last comment, this seems like you are comparing different pipelines. So the Campanella's pipeline of MIL was not considered here. that could have been added as well for the comparative analysis, that which approach works.
Okay.
Yeah.
I will take a note of it. Thank you.
Okay, brilliant. So I think with that, we're already 6 minutes over. So I think we can finish it there, unless there's any burning questions. Doesn't seem like it. So I think
Alex has some questions.
Yeah, if it's okay, just for the results from ResNet and from the vision transformer. So just that I understood it correctly, were it like expert annotations that were used, or did you use the overall, so the slide level label?
Can you just repeat your question? Sorry, I didn't understand.
For the results, you had a slide with the results, and there you also had results for ResNet and for the vision transformer. And I was wondering whether the annotations were expert level annotations, or whether that were also the labels you used for the whole tissue slide.
These are patient level, actually, the results. So it's somehow we aggregated the tile-wise scores to the somehow patient-wise scores, and then we calculated the results.
Okay. Yeah, thank you, and sorry. Yeah.
You're welcome.
no need to apologize. Always welcome. Okay, well, thanks again, Narmin.
That was great. Pleasure. Thank you.
So yeah, thanks so much for giving the presentation, and hopefully many of us will see you in person soon at some
hopefully
event. Yeah.
Yeah, exactly.
Thanks again.
Then I wish you all a nice evening.
And you.
Ciao. Bye bye.
Thank you. Yeah.